In this lesson, we're going to discuss the fundamental theorem of calculus. Suppose we have a curve and we zoom in on that curve in a very small region. So for instance, here's my zoomed in region. The blue curve itself is f of x. And this is just 2 points that happen to be along the curve. I'll say x1 comma f of x1, and up here x2 comma f of x2. Now, if I look at these points, there is a certain distance that's been moved from one point to the other. So from here over to here, from x1 over to x2, that's a distance of delta x, because we've defined delta x as a change in the x direction, x2 minus x1. Similarly, this change from here to here, this is my change in y, so I'll call that delta y. It's f of x2, which is y2, minus f of x1, which is y1. Now, if I'm looking for the slope of this curve, looking at secants first off, then I effectively take this line connecting those 2 points and I calculate the slope of that line. So the slope of this line is going to be, the slope of that secant line is going to be delta y over delta x. So I have the slope of a secant line as change in y over change in x. Remember, we took this and we worked our way into a derivative. We had dy over dx and got a tangent line at a particular point. But this is okay for my purposes right now. Consider the exact same function on the exact same zoomed in region. Along the base, this is still delta x, and along the height, this is still delta y. In another instance, what we did is we tried to find the area underneath the curve, and we found the area underneath the curve by finding the area of a rectangle. So that rectangle in this case is this region. Notice that it's an over approximation because I haven't done a limit to get a perfect area under the curve. But to find that, I find the area by taking the length of that rectangle times the height, which is delta x times delta y. Now consider that for a second. The two basic units that we have, delta x and delta y, are either multiplied together to give us the concept of integration, or divided to give us the concept of derivatives. That's pretty substantial. That tells me that since area and tangent lines are related fundamentally through these delta y's and delta x's, which are just either multiplied or divide, we can make an assumption here that isn't that much of a leap, that these two operations are somehow related to one another. And that's our job in this section, is to see exactly how these two operations are related. So I'm going to state for you the fundamental theorem of calculus, and then I'm going to work through the proof of it. Not all instructors do the proof of the fundamental theorem. I want you to leave this video with the knowledge of exactly why the fundamental theorem works and exactly how sensible it actually is if you look into why it works. So let me state it and then we'll build from there. So if f is a continuous function on an open interval, then the derivative with respect to x of the integral, the definite integral from a to x of f of t dt is f of x. Now, if you've taken a calculus class in the past, this probably isn't the fundamental theorem of calculus that you're thinking of. You're probably thinking of the one that tells you how to evaluate integrals. That's called the second fundamental theorem of calculus. And actually, different textbooks call different ones the first and different ones the second. I'm going with this because this right here, I think, is an extremely important result, which leads to the second fundamental theorem. What this statement does, it establishes three basic principles for us. One is that integration and differentiation are inverse operations, because the statement of this rule tells me that if I integrate a function with respect to some variable, and then I differentiate that, then I end up with the original function that I integrated in the first place. So they've undone each other, so they're inverses. Secondly, every continuous function has an antiderivative. It may not be an elementary function, but every continuous function has an antiderivative. And third, every continuous function is the derivative of some other function. So let's look at these in a little bit more depth here. First off, the notation, the definite integral from a to x of f of t dt is called the accumulation function. So a of x, the accumulation function of x, is the definite integral from a lower bound a to x of f of t dt. Let me show you what that's going to look like exactly. So an accumulation function gives me the value of the area under the curve from a specific starting point up to some other given endpoint. So for instance, the accumulation function of x, we said, was the integral from lower bound a up to x of f of t dt. So if this function right here is my f of t, and what I'm doing is calculating the area under that because I'm doing a definite integral, I've set my lower bound for this particular function to be 0. So I'm going to leave that always as 0, but this upper bound can be different. So a of 1 is the total area under this curve up to 1. A of 1.5 is the total area under the curve from 0 to 1.5. A of 0.75 is the total area under the curve from 0 to 0.75. So it's the total area from some specific starting point to any particular ending point under a function. Now, what we would like to establish is that the accumulation function is the antiderivative of f of t. Because if the accumulation function is the antiderivative of f of t, then the accumulation function and f of x are inverses of each other, or inverse operations to get to them. Let's start out simply here. So we're going to try and establish that the accumulation function is the antiderivative of f of t. So let's begin doing this by working with something that we know. So we know a little bit about derivatives. We know that in derivatives we can use the limit definition of a derivative for calculations. So the derivative of the accumulation function is going to be the limit as delta x goes to 0 of a evaluated at x plus delta x minus a of x divided by delta x. Working with that algebraically, I could write this as the limit as delta x goes to 0 of 1 over delta x times the quantity a of x plus delta x minus a of x. And I haven't done much here. All I've effectively done is moved the term in the denominator and made it a multiplier. Not a big change. But the reason that I did that is because that allows me to rewrite this limit in terms of definite integrals. Because one thing that I do know about this accumulation function is that it's the definite integral from some lower bound a up to the input value x plus delta x of f of t dt minus then the accumulation function of x. Well, I've got a definition precisely of that as the definite integral from a to x of f of t dt. So now I've got a little bit more work completed here. And the next thing that I'm going to do is this. I'm going to rewrite this so that this is now the limit as delta x goes to 0, 1 over delta x times the integral from a up to x plus delta x of f of t dt. And I'm going to change that minus into a plus. And I can do that from a property of definite integrals that allows me to change the sign on my definite integral if I swap the endpoints. So I'm going to make this plus the integral from x to a of f of t dt. Now, the value of a, I'm going to have to assume, but I think it's a safe assumption, that a is somewhere between x and x plus delta x. So if that's the case, then what I can do is combine this into a single definite integral. There was a rule of definite integrals that told me that I could do that, provided the number was in between the two bounds. So 1 over delta x. This can go now from the lower bound of x to the upper bound of x plus delta x of f of t dt. And now what we'll have to do in order to determine what this actually results in is go back to our app to really kind of visually see this. So what I have here is a setup that's given me two accumulation functions for the exact same curve. The reason I set this up is so that you can see that, for instance, the first accumulation function, let's say I allow it to calculate from 0 to 1. Okay, so that's the start and end point for that accumulation function. The second one, I'll just go slightly beyond 1, like 1.04 will be fine. So that gives me some delta x to work with. So delta x here is 0.04. And I can easily calculate the height of the curve at these particular points. So this would be f evaluated at 1, and this would be f evaluated at 1.04. So this would be y sub 1 and y sub 2. I could come up with the value of a rectangle that would give me the area of that particular curve. But what I'm actually interested in is finding the value of this limit as delta x goes to 0 of 1 over delta x times the integral from x to x plus delta x of f of t dt. So this right here, the integral from x to x plus delta x is effectively that green area. So if I could calculate that green area, which we could come up with it, then I took that area and divided it by 1 over delta x. Or not divided by 1 over delta x, but just divided by delta x. This is, in a certain way, almost like it's calculating an average value. So if I were to take some of this data and put it into this limit, I would be looking at the limit as delta x goes to 0 of 1 over, and in this case I have delta x, which is 0.04, and then I'm starting the interval at 1 and then going to 1.04 and calculating f of t dt, which is the area under the curve. So I'm looking at this green region and then dividing it by 0.04. And if I decrease that difference between, effectively what's going to happen is this is going to give me, so I'm taking the area of this rectangle and dividing, I'll write it out here. So I'm taking the area of a rectangle, which originally is base times height. And I'm calculating the area through the integral. The base is delta x. So if I take the area divided by delta x, which is this term right here, what this is doing, so I'm dividing it by the base, that gives me the height of the curve. So this is effectively giving me like an average height within this small interval. But as I decrease delta x back to the first value, the original number 1, then what happens is this limit results in f of x, just whatever the height of the curve is at that original point. So this limit results in f of x. And if that's the case, then what we've learned from the starting point here to the ending point is that a prime of x is equal to f of x. And if you have a function and you take the derivative of that function, it gives you the original function, then what that means is a of x is the antiderivative of f of x. Now, a couple of things that I would like for you to recall about derivatives is, first off, is that if your derivative is positive, that tells me that the original function is increasing. And if the derivative is negative, then the original function is decreasing. So let's look and see if those properties hold here intuitively for the accumulation function and some particular function f. So let's say, for instance, I have a function that is entirely positive. So if I have a function that's entirely positive on an interval, such as this, I'll call this f of x, and then I have some start of my interval a and end, which is b. Oh, actually, I want to bring that a little bit closer. I knew that would happen. I'll make this, actually, I'll call this x so that it looks more like an accumulation function. So the total area accumulated under the function from a to x is this total region right here. So that is a of x. Now, if we increase x by some specific value, so if we increase it by some delta x, what that does is it increases the total amount of area between a and that value. So now this total green area is a of x plus delta x. And clearly, a of x plus delta x is going to be greater than, greater than a of x. So what that means is whenever your function is positive, your accumulation function is increasing. So if a of x is the derivative of f, that needs to hold. And it does. Okay. Here's another concept. So let's say we have a function which looks like this, and some starting point I'll call a, and some ending point over here which I'll call x. Then the total area underneath the curve here is the sum of these two regions. So what happens then is this part is positive area. This part is negative area. And when you combine positive area and negative area, they cancel each other out. So if I increase the value of x slightly to x plus some delta x, that's going to increase the size of my region, but it increases the amount of negative area, which actually decreases the total amount of area altogether. So the accumulation function will be decreasing whenever a function is less than 0. All of this together establishes these two things. The accumulation function is the antiderivative of f of x, and f of x is the derivative of the accumulation function. And since we defined the accumulation function based off of that definite integral within the second fundamental theorem, we can say here conclusively that the operations of differentiation and integration are inverses of one another. That's a huge result. Now, apart from that, there's another result that's really important, which is called the second fundamental theorem of calculus. If f is continuous on the interval from a to b, and capital F is an antiderivative of f, then the definite integral from a to b of f of x dx is capital F evaluated at b, so the antiderivative evaluated at the upper end point, minus the antiderivative evaluated at the lower end point. We're going to go through a proof, and then we're going to go through some intuition of this, because this is a major result and you really need to understand on a fundamental level how exactly this works. So let's start with a proof. All right, so part one of the fundamental theorem guarantees that an antiderivative exists we have a continuous function. All right, it says that we have a continuous function on a to b. So part one of the fundamental theorem says antiderivative exists. So we can define some function g of x, which is the accumulation function from a to x of f of t dt. All right, so this exists. When you have a continuous function, that's guaranteed. Okay? Now, if f is any antiderivative. Okay, difference here is, just so you know, g exists. There's an antiderivative that exists. We don't know what it is at this point, but it exists. Now f, capital F, is going to be any antiderivative for the function lowercase f. So if capital F is any antiderivative of the original function f, then what f has to look like is g of x, but it could only be off by some added constant. So these two functions have to be equal to each other, but it could be off by an added constant. Okay? Now, if I looked at g evaluated at the upper endpoint minus g evaluated at the lower endpoint. So if I kind of skip ahead to the other side of this equality statement. So if I look at the antiderivative evaluated at b minus the antiderivative evaluated at a, this would be the accumulation function evaluated from a to b of f of t dt minus the accumulation function from a to a of f of t dt. And there's something important about that second part. So we know that that second part right there would have to be equal to 0, because there's no accumulation of area from a to a. So that's just equal to 0. But in another respect, we also have that g of a minus g of b could look like f evaluated. Did I say the a and b backwards? I think I did. So g of b minus g of a could be seen as f of b plus c. Oh, minus c, because we would subtract it over, but it's going to disappear in just a second anyway. Minus f evaluated at a minus c. Alright, so the negative distributes allows me to cancel out this c. So this right here, then, since g of b minus g of a is equal to what I just established, and what I said a second ago, we have the integral from a to b of f of t dt is equal to f of b minus f of a. And that proves the fundamental theorem. But I not only want you to see the proof, I actually want you to understand what's happening on a fundamental level. So I'm going to walk you through a little bit of intuition here. Okay. I'm going to go pretty far back in mathematics here to the relationship between distance, rate, and time. Most everyone knows this formula pretty well. It's that distance is equal to rate times time. And I'm going to use that as my basis for your understanding of this fundamental theorem of calculus. Okay? Suppose, well, there we are. Suppose a car is traveling at a constant rate of 20 miles per hour for 2 hours. What distance did they travel? Well, that's not that difficult of a question to answer. We don't need calculus for it. All we really need is this distance equals rate times time. Because we know, and you've solved these kinds of problems before, I'm sure, if you have a car that's traveling at a rate of 20 miles per hour, for 2 hours, so rate times time. The time cancels out, so hours disappears, and you're left with 40 miles. Okay? But then you might be wondering, what does that have to do with calculus? What does that have to do with what we're talking about in the fundamental theorem? Well, let's see what that has to do with the fundamental theorem. Now, if I have a function representing the speed or velocity of this car, whatever you want to call it, then the velocity is constant. It's 20 miles per hour. So whenever this car begins, somehow it's already going 20 miles per hour, and it just stays going 20 miles per hour forever. So 1 hour passes, going 20 miles an hour. 2 hours pass, going 20 miles per hour. This car stays at a constant rate of 20 miles per hour. Let's take a look at what it means for that 40 mile. Where is that 40 miles in this example? So here's the end of my 2-hour interval. If I multiply 20 and 2, when you think about where these numbers come from, the height of this curve is 20. And in fact, it's actually the difference between 20 and 0, so you can even think of it as a delta y. The width of this interval is 2, because the end time is 2, the start time is 0, 2 minus 0 is 2. When you multiply those together, here's something I want you to understand. I've said this before, but I'm going to say it again here. Whenever you do something algebraically, there's something happening behind the scenes geometrically, whether you choose to see it or not. But if you do choose to see it, it actually helps you unlock a lot of the mysteries of mathematics. Here's one of those mysteries that we're going to unlock. I'm multiplying together 2 times 20, and what that enables me to do is find how far the car traveled, which we know is 40 miles. But when I multiplied those two numbers together, I measured the area of this rectangle. So somehow, the distance is the area of a rectangle. Okay? And you can see it right here. That's exactly what's going on. And I want you to keep that in mind, because we're going to go to another example where things are just slightly more complex. Suppose we have the same car, but it increases its speed at a constant rate of 20 miles per hour over the same 2-hour period. Now we want to know how far the car travels in 2 hours during this time period. Right? Well, so the car is increasing its speed at a constant rate of 20 miles per hour. I probably should have said that this starts from rest. Okay, but I meant for it to. The car starts from rest, and it increases its speed at a constant rate of 20 miles per hour. So at the end of the first hour, it's now traveling 20 miles per hour. At the end of the second hour, it's traveling 40 miles per hour, because every hour traveled increases its speed by 20 miles per hour. So it's a constant rate of change. So now we want to know how far does the car travel in these 2 hours. Well, we could use distance equals rate times time, but it's no longer going to be an exact answer for us. It's only going to be an approximation. So for instance, this function right here is my velocity function. So the velocity of the car is 20 miles per hour times however many hours it travels. Okay, so my velocity is linear. In the first hour, I could approximate the distance traveled. So I could say the distance traveled is approximately, if we look in the first hour, I could take area of this rectangle, and I could find that using distance equals rate times time. So the rate in the first hour times the amount of time. Okay. In order to do this, I'm going to use the rate of speed at the end of the first hour, just for simplicity. So here's the rate is the velocity at the end of the first hour times the amount of time at that hour, so 1 hour. That's going to give me this amount of area right here. But the car traveled another hour, so I would need to take the rate in that hour times how long we were going that rate. So again, I'm just going to use the end point of the interval as my estimate for what speed was traveled. And so if I multiply that times 1, which is the amount of time traveled there, so v of 2 times 1, then that would give me the total amount of distance traveled in that hour. So the distance now would be, so the velocity at the end of the first hour is 20 miles per hour plus 1, or sorry, times 1, plus the velocity going at the end of the second hour, which is 20 times 2, which is 40, times 1. When we add this together, that gives me an estimate. Remember, this is only an estimate to how far the car traveled, but 60 miles. Okay. So as long as we all still agree that distance is that area of the rectangles that I've added together, then we can do this. We have an estimate to how far the car has traveled in that particular time period. Now you may be thinking to yourself, you chose to use the speed at the end of the first hour. He was clearly not traveling 20 miles per hour during that entire interval. And I would understand your discomfort with that. But what we could do then, if we wanted a better estimate, is increase the number of times where we test to see how fast the car is traveling. So for instance, same velocity equation, so v of t equals 20 times t, and I'll go from 1 hour to 2 hours. Okay, but let's say instead of using just 2 points here for testing, let's say I increase it to 4. Wouldn't that provide a better estimate to what the total distance traveled would have been, because there would be less error in calculating using rectangles? So it still would be an estimate, because calculating the distance based off of this, we can clearly see that there's still some error. So like for instance, when I take the first interval here, which is 1/2 of an hour long, and multiply it by the height of the function, which would be the velocity, the total distance traveled there would still be slightly more than what we needed. But it's still determined by a rate times time. So the rate at the end of the first hour, I'm sorry, the end of the first half hour this time, times 1/2 hour. Okay, then it's going to be the velocity at the end of the first hour, so it would be this height here, and then when we multiply that by that half hour, it measures out the area of this rectangle, calculating a distance. And then when we do v at 3/2 times 1/2 plus v at 2 times 1/2, then what happens is we get the remaining intervals here and here, adding up these areas. When we calculate, let's see what we come up with. So the velocity 1/2 hour would be 20 times a half, which is 10, but that's still times a half, plus 20 times a half, plus 3/2 times 20 would be 60 over 2, which would be 30 times a half, plus 40 times a half. All right, so 5 plus 10 plus 15 plus 20. 20 and 10 is 30, plus another 20 is 50. So now we have an estimate of the car traveling 50 miles, which is a slightly better estimate because there's less error here. And I know that there's less error because the previous estimate also included this region and this region. So it at least knocked off that amount and got a better estimate. And if we continue to increase the number of rectangles, I think you can see where this is going. We're going to get a better and better estimate until we get to the point where we have enough rectangles where we can actually take a limit and we can get the actual distance that the car traveled. Okay, that I want you to understand. Let's move on to another question. Now, suppose the same car travels in such a way that it starts from rest, increases its speed to some maximum value, then decreases back to rest in a 4-hour period. And I don't know why I chose to bring this back to make this a 4-hour period as a term, as opposed to a 2-hour. I just liked the graph better, but honestly I could have rescaled. It doesn't really make a whole lot of difference. So, what I think you can see, however, is if I wanted to get the total distance traveled by the car in this time period, then what I would need to do is come up with a function, an accumulation function, so I think you can see that if I wanted to find the total distance that this car has traveled, that is going to be equal to the area under the curve. Okay? And I could come up with that area under the curve by using the limiting process, using rectangles, getting better approximations, that sort of thing. That's not what's important right now. What is important is I could also even define an accumulation function. So if I defined an accumulation function such as s of t equals the integral from 0 to x of v of t dt. So if this function right here is my v of t now, so it's my velocity, then s of t, whatever x is, it is the total area from 0 up to x of this particular function. So I've now got this accumulation function defined. Okay? And my accumulation function right now starts at 0. But 0 is a nice reference point, but suppose we start at some value a instead of 0. Okay, so this would be a, and this would be x. I can effectively call x the endpoint of an accumulation function that goes from 0 up to x. So this total area right here is defined by s of b. So in green, I have the accumulated area under this curve from 0 up to b. A going to be in red. It's the accumulated area from 0 up to a. So from 0 up to A. That's that region right there. Now what I want you to understand is that the total area under the curve between A and B, so let me just go ahead and tell you what, I'll scratch out X and make it B. Okay, and you know what, I'll even make A red just so that it, well, that there, A is red. The total area under the curve is now S of B minus S of A. So S of B is the green region. If you subtract out the green region, if you subtract out the red region from the green region, what you get is the remaining blue region, which is the total area from A to B. So that's S of B minus S of A. And further, S of B minus S of A is the accumulation functions 0 to B of our velocity dt minus 0 to A of our velocity dt. That's just exactly how we defined S of B and S of A. So the green and red stars there, which I could rewrite knowing that the lower endpoints, if I swap the endpoints of an integral, so the endpoints from 0 to A, if I swap them, I can make this a plus in between them. So now if 0 here and 0 there, they're the same number. So what I can do then is combine that into a single integral, provided that 0 is between those values, and it becomes the integral from A to B. And you might be thinking, wait a second, 0 is not between A and B. But when you reverse the interval from A to 0 instead of 0 to A, it's like A is back here, so 0 is between them. Don't worry, it works out. But anyhow, it works out that this is the integral from A to B, v of t dt. So, for any function that is an antiderivative of f of x, we have the integral from a to b of f of x dx can be evaluated as the antiderivative at the upper end point minus the antiderivative at the lower end point, and that right there is the fundamental theorem of calculus. That will make our work so much easier, because from this point forward we no longer have to do Riemann sums in order to get exact areas under curves. We can use antiderivatives to do that, and that's really going to help us out in the future. Let's see some examples. I think you'll find the way that you do the examples are much easier than the way that you actually work through proofs of things. But once you've proven it and established it, the fundamental theorem is generally pretty straightforward to work with. So I have the integral from -1 to 3 of x cubed plus 1 dx. So what the fundamental theorem says is to find an antiderivative. So the antiderivative of x cubed plus 1, we will add 1 to the exponent, divide by the new exponent. The antiderivative of 1 is just x, and then we evaluate from -1 to 3. This is generally the notation used here, just a vertical bar indicating that we haven't evaluated yet, but we need to. If I plug in the 3, that's going to be 3 to the 4th power, which is 81 over 4, plus 3, then minus -1 to the 4th power is just +1, so 1/4, and minus 1. Let's see. 81/4 minus 1/4 is going to be 80/4, which will reduce to 20 in just a second. 3, this is going to be minus a negative 1 because this negative makes this a negative 1/4 and this a positive 1. So then that's effectively plus 4. So 20 plus 4 is 24. So the total area under this curve, the total exact area under this curve, is 24 units. And even though we don't know a formula that would geometrically calculate the area under a cubic style curve, this method of integration doesn't require one. Here's another example. The integral from -1 to 2 of 7 minus 2x dx. If I find the antiderivative first, that would be 7x minus x squared over 2. The 2's cancel, so that's just 7x minus x squared, evaluated from -1 to 2. Then if I plug in 2, I would have 14 minus 4. And if I plug in -1, it's -7 minus 1, because when you square -1, it becomes positive, so it's still negative here. Alright, 14 minus 4 is 10. And then it's minus -8, so 10 plus 8. So we get a total area under the curve of 18. Here's another example. In order to work this out, we need to rewrite the integral just a little bit before we actually perform the integration. The square root of t is the same thing as t to the 1/2 power. And what I'm going to do is distribute that t to the 1/2 power into these parentheses. So t to the 1/2 times t would be t to the 3/2 power. T to the 1/2 times 1 would be t to the 1/2. And now I have something I can use the power rule on for anti-differentiation. T to the 3/2 is going to be, when I integrate, t to the 5/2 over 5/2 plus t to the 3/2 over 3/2. And all of that's going to be integrated, or we should probably say evaluated, between 0 and 1. Let me take care of those fractions as I go through this. So this would be 2/5 of 1 to the 5/2 power. 1 to any power is still just going to be 1. So this is just going to be 2/5. Likewise, this will be plus 2/3. Then if I plug in 0, even though this 5/2 power might be intimidating, 0 to any power is just 0. So this is effectively 2/5 times 0 plus 2/3 times 0. This whole term over here is just 0. It's not a big deal. All we have to do is work out the fractions in the first one to get our final answer. So 15, I had to multiply by 3, so that will be 6/15. And then this one, denominator, needs to also be 15, so 10. So it looks like 16/15, or just a little bit over 1. And I've got plenty of examples here. I'll roll through them for you. Integral from 0 to pi of 2 plus cosine x dx. So here we're just integrating, finding an antiderivative using trigonometric formulas. That's the only difference in this one. The integral of 2 would be 2x. The derivative of cosine is negative sine, so the integral of cosine is going to be positive sine. So that'll just be 2x plus sine x. Then it's going to be evaluated from 0 to pi. which would be 2 pi plus sine of pi minus 2 times 0 plus sine of 0. The sine of 0 is 0, so effectively everything in this parentheses becomes 0. And then the sine of pi is also 0. So what this means is my final answer is just 2 pi. Here's another one. The integral from 1 to 2 of 4 over x dx. Now, this particular example, don't be thrown off by the integral of 1 over x. It's not one that you can rewrite as the power rule and then integrate. It's the natural log function. So this would be 4 times the natural logarithm of absolute x evaluated from 1 to 2. Now the absolute value isn't all that necessary in this example because we know that the values we're going to evaluate from are positive. So that's okay. 4 times the natural log of 2 minus the natural log of 1. And the facts that you need to know about natural logarithms, any logarithm evaluated at the point 1 is equal to 0. So this just evaluates to 4 natural log 2. Next up, we're going to talk about the mean value theorem of integrals. So when we talk about the mean value here, we're actually talking about the mean as an average. So recall how we define the average for a set of numbers. So if we have just any set of numbers, x1, x2, x3, x4, and so forth, out to x sub n. The average of these numbers is the sum of all of them, so we start adding them together. And then we divide by the number of values that existed, which in this case would be n, just whatever the last subscript would be. Which could look like the sum from I equals 1 to n of x sub I divided by n, which is the same thing as a sum from I equals 1 to n of x sub I times 1 over n. And if you consider delta x to be 1 over n, that looks an awful lot like the area of a region. It looks a lot like an integral. And it turns out it actually is. So we can use the concept of integration through different types of applications. It doesn't just have to be areas under curves. Here we can actually get averages of functions. So consider the function f of x equals x squared plus 2 on the interval from 0 to 8. What we can do is we can estimate the average value on different subintervals. I'm going to pull up an application to make that a little bit easier, but the idea is just exactly this. So if I use a couple of subintervals, not a whole bunch, just for simplicity's sake. The height of this function is defined as f evaluated at 8, which would be 8 squared plus 2, which is 66. The height at 0 is going to be the value 0 squared plus 2, which is 2. So initially, the average value, so x bar, would look like the start value of 2 plus 66 divided by 2, because that's how many values we used. And 2 plus 66 is 68. When we divide that by 2, we get 34. So the average value of that function looks like 34. And that's just using 2 sample points. If I used another sample point, so if I split this interval up into another value here, let me just say if I used four as my next test point. So then I need to calculate the height of the function at 4. 4 squared is 16, plus 2 is 18. So then the average now would look like 2 plus 18 plus 66, which you might be thinking, this is going to be strange, it's not going to work out because now I have 3 numbers added together. How in the world is that going to result in anything meaningful? But I'm now dividing by 3 as well. So I'm not just using the sum in the numerator. So this average value, using 3 points, would be 2 plus 18 plus 66. Then if I divide that by 3, I come up with 28.7. And I could use 4, 5, 6, I could use a whole bunch of different test points. And the more I use, the better estimate that I'm going to get. Let's pull up an application so that the computations can be done a little bit faster. Okay, so here I have the same function on the same interval, 0 to 8. I have 2 values used. Notice the average value is 34. If I increase the number of test values, so if I go up to 3, then I'm using 0, 4, and 8, just equally dividing. Now I have the average value calculated of these points here. Okay. If I take the average value of those y values, I get 28.7, just like I did a second ago. If I increase to 4, I've got 26.89 and 26. The more points that I use, the more subintervals I use, the better approximation I get to the average value of the function overall. So the question is, does this actually come out with a limit? Is there a limit to this? Or does the average value keep changing forever? Turns out that if we continue increasing the number of test points, these things actually do come out to a limit. And that limit, I can show you here, in this particular case, is 23.3. Alright, so the thing is, if I have an average value of 23.3, if I have an average value of 23.3, effectively what I'm saying is the rectangle here is at height 23.3. This should be the same amount of area in this rectangle as there is under the curve. So the area of this rectangle should be the same as this area under the curve. We're going to walk through some details of the proof of that, but the important thing to know is that you can get the average value of a function through some means. So let's walk through determining what that means is. Okay, so as I said, if you continue doing subdivisions, you can eventually take a limit to get the actual average. So the average of some function f of x is going to be the limit as the number of subintervals increases to infinity of the sum from I equals 1 to n of each of our test values, so f evaluated at x sub I, times 1 over n, the number of subintervals that we have. Now that right there, what I can do is change it a little bit, multiplying top and bottom by b minus a. Here's the reason I'm going to do that. The reason I'm going to do that is because this then becomes 1 over b minus a. So I'm going to take the b minus a that's in the denominator here all the way out, make it a multiplier on my limit. Okay? So that's then going to be 1 over b minus a times the limit as n goes to infinity of the sum from I equals 1 to n, f of x sub I. Now I have b minus a over n. b minus a over n is the width of our interval divided by the number of subintervals. That is exactly how we define delta x. Now this thing right here, that is exactly the definition of my integral. So then the average value of x is 1 over b minus a, so 1 divided by the width of my interval, times the area under the curve from a to b of f of x dx. So this is how we actually compute the mean value of a function over a specified interval. Now I want you to consider what this means. So this is the area under f of x on the interval from a to b. Okay, so we know what that would look like. Here's some function f of x. Here's some interval from a to b. Okay? Now, that integral is the total area under the curve from a to b. We've established that well enough at this point. The width of this interval is b minus a. Okay? Now, here's the thing. We're saying that that area is equal in area to some rectangle which has a base of b minus a, but some unknown height. Okay. However, the area of this rectangle is the area from the integral from a to b of f of x dx. So what we can determine then is, since area is length times height, or length times width, whatever you want to call it, it's two things multiplied. The area, which is the integral of a to b of f of x dx, is the length, which is b times a, times the height. And if you solve for that height, you get 1 over b minus a times the integral from a to b f of x dx. So this average value gives you the height of a rectangle that is equal in area to the area under your curve. It's almost like you can take a region under any function and decompose it into a rectangular region of the exact same size. And that's a pretty powerful thing we could do there. But what you need to be able to do is evaluate these. And evaluation is really no big deal. If you want to find the average value of y on the interval from 1 to 4, you take 1 over the width of that interval times the integral from 1 to 4 of 3x squared plus 1 dx. So this would be 1/3 times the integral of 3x squared plus 1. That would be 3 times x cubed over 3, which is x cubed, plus x, evaluated from 1 to 4. So 1/3 of 4 cubed is 64, plus 4, minus, plugging 1 in, it's just 1 plus 1. Oops, had a bracket there instead of parentheses. So this is now 1/3. 64 plus 4 is 68. 1 plus 1 is 2. So this is 1/3 of 66, which is 22. So that right there is the average height of our function on that interval.